Welcome back, everybody. In this video, the plan is to cover a handful of questions related to probability and the normal distribution. And in some of the problems, we will be simply transforming scores into z-scores, so we'll be standardizing them. But in other questions, we will actually be using the unit normal table, the z-table, to identify specific proportions associated with normal distributions. So let's get into it. Starting with this first problem, transform the following population of 6 scores into standardized z-scores. So that just requires us to use one of the two z formulas. Z is a formula that standardizes any x value based on distance from the mean in terms of standard deviations. So it tells you how many standard deviations, either above or below the mean, any individual score actually is. And in order to do this, you need the mean and the standard deviation. And so that's our first step. Let's go ahead and do that. It's always good to practice. So first things first, let's just list out our scores in a row. And we sum them together, and we get 18. And therefore, the mean is 18 divided by 6, which is 3. All right, so to calculate the standard deviation, which is a measure of variability, we use the formula right here. Standard deviation equals the square root of SS over n. I'm using this formula because it is a population of scores. Of course, note that if it was a sample, you need to use one of the sample formulas. All right, so step 2 in my series of steps is create a column where you are calculating the deviation score of each individual x value. So how far each x value is from the mean. So 0 minus 3, 6 minus 3, 5 minus 3, 2 minus 3, 3 minus 3, and 2 minus 2. And as you know by now, if you add up those values, and I'm actually looking at them, it looks like I wrote this one wrong, so here's a little typo I'm going to fix. 6 minus 3 should be 3. It's always possible I'm going to make mistakes in these videos. Please email me so that I can let the class know if I've made a mistake. That's always helpful. But anyway, the reason I knew I made a mistake was because these values, these deviation scores, should always add up to 0. So on the exams, for example, make sure you're adding these together, and it should add to 0, which it does now, so we're good. The next step, square those deviation scores. So I'm taking each individual deviation score and squaring it. -3 squared is 9, 3 squared is 9, 2 squared is 4, -1 squared, 0 squared, and 1 squared. All right, we're almost there. Add these together, gives me sum of squares, which is 24, and therefore the standard deviation is the square root of 24 over 6, and 24 over 6 is 4, square root is 2. All right, so we have what we need now. We have all of the individual x values. Those were given to us. And we just calculated the mean and the standard deviation. So now we can transform each of those scores into a z-score. So we have to do it 6 times. Let's start with the first one. Z equals 0, that's the first score. Subtract the mean, which is 3, and then divide by the standard deviation, which is 2. And that gives me -1.5. In other words, an x value of 0 becomes a z value of -1.5 when the standard deviation is 2 and the mean is 3. That's all there is to it, just applying this formula, plugging things in. Okay, the next value is a 6. So to calculate the z value, we take 6, subtract the mean, and divide by the standard deviation. That gives me 3 over 2, which is 1.5. The next z value, I'm going to put some crosses here so it makes these z's more apparent. The next z value is, the next x value is a 5. So 5 minus the mean of 3 divided by the standard deviation gives me 2 over 2, which is 1. The fourth value is a 2. 2 minus 3 over 2 gives me negative 0.5. The fifth value is a 3. 3 minus 3 divided by 2 is 0. And then finally, the last value is a 2. 2 minus 3 divided by 2, negative 0.5. And there you have it. We have transformed these 6 scores into standardized scores, standard scores, also known as z-scores. Okay, so that's problem number 1. Let's look at a new problem here. And this new problem is going to ask us to identify proportions associated with this normal distribution. So the normal distribution, hopefully you have read this by now, it's the bell curve. And it's characterized by symmetry, so it's the same on both sides. And it is largest in the middle because the mean, the median, and the mode are all equal, and they're right here in the center. And this right here is called a standard normal curve. I know it's standard because of these values down here. These are z values. So a z value tells you distance from the mean, and thus the mean of z is always 0 because the mean is right in the middle. And therefore 1, this value is 1 standard deviation above the mean. This value here, negative 1, refers to the point that is 1 standard deviation below the mean, and so on and so forth. So this first question says what proportion, or I guess the second question here in our video, says what proportion of scores in a normal distribution is 1.5 standard deviations below the mean or less? All right, so these are the standard deviations that are below the mean because they're negative. The mean is right in the center. And it's asking about 1.5 standard deviations below the mean or less. In other words, I find the point that is negative 1.5. Let me make this a little clearer here. Yeah, I guess hopefully that's legible. Negative 1.5 is about right here. And I'm going to sort of shade in this entire section that I'm interested in. How do I know this is the part I'm interested in? Because the question reads, or less. So lower numbers are below this value of negative 1.5. Even though it's a positive 1.5 over here, what's important is it says 1.5 standard deviations below the mean. If it was above the mean, it would be up here, but below the mean is a negative 1.5. And now what we need to do is go to our table, the unit normal table. And recall from the module, there's these different columns depending on which part of the actual curve you're interested in. So shading this in, I identify this as the tail. And that means that I will find that proportion in column C, which is the tail column. But before I get there, I want to show you how this question would be written in notation form. It would look something like this. It's what's the proportion of z values that is less than negative 1.5. So this notation is saying the exact same thing as this in words. And on an exam, for example, you might see it both ways. So be sure to practice problems that have both ways of going about these types of questions. Okay, anyway, here's how we solve this problem. I go to my table and I find a z value of 1.5. So column A has all the z values. Here it is on page 3, a 1.5. There's no negative values listed because the table is, the bell curve is symmetrical. So all of the proportions associated with 1.5 are the same as the proportions associated with negative 1.5. Anyway, I find 1.5 in column A. I simply go to column C, the tail column, and there it is, 0.0668. That's it. So 0.0668 is the proportion of scores in a normal distribution that is 1.5 standard deviations below the mean or less. And in percentage form, you would multiply by 100 to get 6.68% of scores. Okay, so let's start to look at some additional types of sort of ways that this could be asked. So in this question, number 3, slightly different. It says, what proportion of scores in a normal distribution is 1.5 standard deviations below the mean or more? So it's going to look like this. What proportion of z-values is greater than negative 1.5? So negative 1.5, again, is the point that is 1.5 standard deviations below the mean. But now we want to know what is the proportion of scores that is larger than that point. So I'm shading in everything to the right, this entire section, as opposed to in the last question, which was less than negative 1.5. So now this is the body, because it has one of the tails, but also over 50% of the entire curve. So we identify that as the body. So I go to my unit normal table. I find a z-value of 1.5, even though it's negative 1.5 that I'm interested in, and I go to the body column, column B, 0.9332. That's the proportion. And in percentage form, 93.32% of scores are 1.5 standard deviations below the mean or more. Interestingly, if you added up the answer from number 2 and number 3, you get 100%, because what we had here was the first, the question right before this was less than this value. This question is greater than. So combined, you have the entire curve. You have 100% of all scores. Okay, moving along, I'm going to erase this and go back to this. So a new question. What proportion of scores in a normal distribution, that's a typo, let's fix that just for my neurotic tendencies. And here we go. So what proportion of scores in a normal distribution is between the mean and 0.75 standard deviations above the mean? All right, so now we have something a little different as well. This is asking us what proportion of scores is from the mean, which is right in the center, to this point, let's say right about here, 0.75. And all we care about is the proportion in between. So this is not a column, this is not a tail, this is not a body. This requires us to use column D on the table. If you look at column D, it says proportion between the mean and z. And that's what we have. The mean is the middle. This z is 0.75. In notation form, it's going to look like this. What proportion of z values is between 0 and 0.75? All right, so I go to my table, identify a z value of 0.75, and then I scroll over to column D, and I find it the proportion is 0.2734. In percentage form, 27.34% of all scores in a normal distribution are between the mean and 0.75 standard deviations above the mean. All right. So at this point, we're going to sort of change gears and apply what I would consider more real-world applications of normal curve and probability questions. So our fifth question here is something like this. The mean cholesterol level in children is 175 milligrams with standard deviation of 35. Assume this level varies from child to child according to an approximate normal distribution, the bell curve. What proportion of children have a cholesterol level above 200? Okay, so what makes this problem slightly different is that we are working with x values instead of z values. In other words, we are talking about actual scores. We're talking about cholesterol levels here. In order for us to find the proportion associated with various amounts of cholesterol, we have to transform these scores, or x values, into z values. Because the table, the unit normal table, lists the proportions associated with standardized values, which are z-values. So everything must become standardized to read this table. And so that's our first step. Convert this value of x equals 200 into a z-value, so then we can go to our table. We do that using the formula for standardization. So here we go. Z is equal to our x value of 200, subtract the mean of 175, and then divide by the standard deviation of 35. So we get 25 on top in the numerator divided by 35 gives us a z-value of 0.71. All right, so essentially what this question is now asking, it says, originally, what proportion of children have a cholesterol level above 200? Well, now it's saying, what proportion of scores in a normal distribution is larger than 0.71 standard deviations above the mean? Because now we're talking about standardization, and that means we can use our table. So 0.71 on the curve is probably somewhere around here. And I'm going to shade in the section that I'm interested in, which is greater than that. So that's everything over here. The reason I shade in, again, is to identify which part of the curve do I care about. This is the tail. And so here's how we're going to solve this problem. I'm going to go to my unit normal table, look up a z-value of 0.71. There it is, column A. And then go to the tail column and find the proportion to be 0.2389. So 0.2389 is the proportion of children with a cholesterol level above 200, or 23.89% of children have a cholesterol level of 200 or higher. Pretty straightforward, but the difference here is that we had to first start with x values and transform them into z values before going to the table. And so the questions can vary. For example, we could have had to go from z values into x values. So let's keep going. Let's look at a few more problems just to get a diverse array of examples of how we can apply probability in the normal curve. So number 6, a forest products company claims that the amount of usable lumber in its harvested trees averages 172 cubic feet. That's the mean. And it has a standard deviation of 12.4 cubic feet. Assume that these amounts have approximately a normal distribution. What proportion of trees contains more than 150 cubic feet? So let's just, do something a little different. One of the ways that you could think about this question is asking what proportion of x values is greater than 150. So we need to transform this x value of 150 into a z value so that we can, again, read the table. But let's do it step by step. So step 1, turn that x value into a z value. So the x value of 150, subtract the mean of 172, and then divide by the standard deviation of 12.4. Let's look at my calculator here. We get negative 1.77. Negative 1.77. All right. Now, if we apply this to the curve down here, let's see. So negative 1.77 is about right here. And what I'm interested in, however, is everything that is greater than that value. In other words, what I originally wrote here with x values in terms of x being greater than 150 can be rewritten as z is greater than 1.77 in standard terms. So I find negative 1.77, and I shade in everything larger than that value to identify which part of the normal distribution that I'm interested in, and that's the body. All right, so here's what we got to do. Go to our unit normal table, find a z value of 1.77, there it is, and go to the body, 0.9616. 0.9616, or 96.16% of trees contain more than 150 cubic feet. Okay, there you have that one. Let's do a couple more. Moving on to question number 7. The mean cholesterol level in children is 175. Oh, so we already had this question. I'm looking at it as a slightly different way. So let's read it again. The mean cholesterol level in children is 175 with standard deviation 35. Assume this is a normal distribution. How high are the levels for the highest 2% of all children? The highest 2%. So in this question, we're starting off with a proportion of 0.02 or 2%. And we have to actually work backwards and find what score, what cholesterol level is associated with that top 2%. So think of it kind of like this, that this shaded in section right here is the top 2% of all cholesterol levels. We want to know, what is that spot right there? What is that point, that X value, which a cholesterol level, which separates the top 2% from the bottom 98%? So what we're doing here, though, is we're going to go first to the tail column of our table and look up 0.02. So find a proportion of 0.02. It looks like this value right here, 0.0202, is the closest value, and I see a z value of 2.05. So z value, this point right here, excuse me, I have to correct this. If I were to treat this point right here as a z value, thank you for your patience, this value right here is 2.05. That is the z value that separates the top 2% from the bottom 98%, but we want to know how high are the cholesterol levels to be in that top 2%. So our final step is to take this z value of 2.05 and turn it back into an x value using your formula. All right, so our z value of 2.05 equals x, which is unknown, subtract the mean, which is 175, divided by the standard deviation of 35. So using algebra, you solve for x. So I'm going to go ahead and do that. Cross multiply 2.05 times 35 gives me 71.75. Add 175. Looks like x equals 246.75. So if you have a cholesterol level as a child of 246.75 or higher, you are in the top 2% of all children for cholesterol levels. Okay, so you're sort of seeing another way these types of questions can be asked. Let's look at one final example. Question 8 this time. A forest products company claims that the amount of usable lumber in its harvested trees averages 172 cubic feet and has standard deviation of 12.4 cubic feet. Assume that these amounts have approximately a normal distribution. What proportion of trees contains between 150 and 180 cubic feet? All right, so the same data we were working with earlier with these trees, but now we want to know the following. What proportion of trees are between 150 and 180 square feet? That's what the notation would look like in this question. Again, as always, we have to take these x values and turn them into z values so that we can use our table. So we have two x values. They both must become z. Here we go. The first one, x value of 150, subtract the mean, divide by the standard deviation. And then I'm going to put the math over here for the second one. The x value is 180, subtract the mean, divide by standard deviation. All right, So let's pause a moment while we calculate this. I guess I'm not going to pause, actually. I'm going to have the video keep playing so that you can watch me calculate something. Very exciting. All right, this first one I'm getting negative 1.77. Sounds familiar to an earlier problem. And then the second one, we get 0.65. Always round to the second decimal place. 0.65. So now, you could almost think of this question as rewritten in terms of standard scores like this. What proportion of z values is between negative 1.77 and 0.65? These are the exact same thing. It's just that over here on the left, this is in terms of x, the cubic feet of a tree. Over here, this is just standard scores, z-scores. But now we have two to worry about. I'm not too worried, though. I think we can all handle it. Put this first one, negative 1.77 here. And then I'm going to put this line in the middle, the 0, because over here I have another z-score, positive 0.65. And I want to know about everything in between those two values. But this is not the body, this is not the tail. We have this middle section, and here's how we're going to solve this problem. I'm going to get a new color here. Let's use red. I'm going to essentially break this proportion into two pieces. The first thing I'm going to look at is from negative 1.77 to the mean. This section right here in red. And then I'm going to add that to this section in black, and together we get the proportion between the two values we care about. Okay, so let's go ahead and do that. This first one, between negative 1.77 and the mean, we need to look at column D. So let's go ahead and find 1.77 on the table and look at column D. There we go, 1.77 in column A, that's our z value. The distance, or the proportion, between the mean and that z value is 0.4616. Now we do the same thing over here. We also use column D, but now we care about a z value of 0.65. This is going to allow us to just identify the proportion between 0.65 and the mean, which is this dark shaded region to the right. So let's go ahead and do that. 0.65. There it is. Scroll over to column D. I see 0.2422. So let's add them together. .7038, which is 70.38%. Okay, so the interpretation here, a proportion of 0.7038 is that's the proportion of trees that contain between 150 and 180 cubic feet, or 70.38% of trees. Alrighty, there you have it. 8 questions related to probability and the normal distribution. If you have any questions, don't hesitate to ask, and hope you have a nice day.